Last time on Mastering AMC 1012, we covered stars and bars and some very interesting examples. But today, we're covering combinatorial identities, starting off with the binomial identity. This basically states that n choose 0 plus n choose 1 all the way till plus n choose n is 2 to the n. Now, why is this true? Well, you can think about n objects. So if we have n objects, the number of ways of selecting 0 objects is n choose 0. The number of ways of choosing 1 object is n choose 1. The number of ways of choosing 2 objects is n choose 2. So on, all the way until the number of ways of choosing n objects is n choose n. We can also count this by noticing that for each object, we have 2 choices. It's either we count it or we don't. So we use a combinatorial proof of this identity to see where this actually comes from. And it's very powerful, and it's very useful in many different AMC and even beyond. So Vandermonde identity. Now this is extremely powerful because it allows you to convert this seemingly complicated choosing expression into just n plus n choose n. How? Well, let's first take a look at what this. It says that n choose 0 times m choose n equals plus n choose 1 times m choose m minus 1. So on. Basically what we're doing is the sum of this and this, the sum of what we're choosing, the number of objects, sums to n. And then we go over all such values. We just iterate. And we get this nice looking expression, m plus n choose n. Now I know this was probably a nightmare to memorize. So let's see where this actually comes from. Basically, let's say that we're trying to select from m plus n objects. Let's say we have m red balls, and n green balls. So what we're trying to do is we're trying to select m total objects. So first of all, how many ways are there to choose m total objects? M. We have m plus n choose objects, so it's just equal to m plus n choose n. Now, is there a different way we can count this? We can have 0 green objects and m red objects. There's n choose 0 ways of choosing 0 green objects and m choose m ways of choosing m red objects. Now, what if we have 1 green object and m minus 1 red objects? M choose n minus 1 red objects choices and n choose 1 green objects. And we can do this for all the values. Basically, we're just taking all the cases of the number of green and red objects, and when we add all those expressions up, it's just the number of ways of choosing m balls from m plus n total balls, which is m plus n choose m. Or if you remember the identity that a plus b choose a is equal to a plus b choose b, because these values sum to the top part, because the reason is because we're choosing a objects to keep, or we're choosing b objects not to keep. They're the same thing. That's why it becomes m plus n choose n over here. Now there's a special case of Vandermonde's identity, and we're actually going to use this in one of our problems. The sum of k choose I squared is just 2k choose k. Now essentially what that is saying is that, look here, we have k choose 0, and then k choose 0 times k choose 0, plus k choose 1 times k choose 1, plus so on, k choose k times k, choose k. Okay, well, what do we know is also equals to k choose 0? K choose k. Remember this thingy over here. So we can rewrite this as k choose 0 times k choose k, right? Now over here, k choose 1. What else is equal to k choose 1? K choose k minus 1. So on. What is equal to k choose k? K choose 0. That's k choose k times k choose 0. Okay, and look at this. That is Vandermonde identities. We've got k of one kind of object and k of another kind of object. And there's 2k objects, we're choosing k of them. There's 2k, choose k ways to do that. Or we can just sum all the choosing products up individually for choosing 0 of one type, k of the other type, so on. And this is just Vandermonde's identity, and this is where it comes from. Now you could memorize these, but I think it's much easier if you just understand the logic behind them, so you can easily figure them out when needed. Okay, next up, we have Pascal's triangle. So Pascal's triangle is just an array of binomial coefficients, which basically means when you expand a binomial like x plus y to the power of n, we end up with a bunch of these terms. And essentially what this is Pascal's triangle represented in choosing notation. But the main thing that's important from Pascal's triangle is Pascal's identity. Now you may be familiar that in a Pascal triangle, the sum of two of the top numbers equals the number on the bottom. Now this actually, based on our choosing diagram here, corresponds to Pascal's identity, which states that n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. An example of this, well, let's see, 5 choose 2 plus 5 choose 3 equals 6 choose 3. Now, earlier, I also used to forget that which way it was, but whether it was n choose k plus 1, n plus 1 choose k, it gets a little bit confusing. So the easiest way to remember this is just to remember that 5 choose 2 plus 5 choose 3 is 10 plus 10 is 20, or 5 choose 2 plus 5 choose 3 is equal to 6 choose 3. And if you ever forget, just try to look at some kind of choosing expression of this form, and you'll easily figure it out if you ever need to use it. So this is very powerful because it allows us to convert two choosing expressions to just one. Sometimes you can stack them up and convert a lot of choosing expressions to very few. Okay, next up, we have the hockey stick identity. Now, the reason it's actually called a hockey stick identity is because if you kind of draw it out here, it looks like a hockey stick, which is actually where the name came from. But the actual math behind it is that the sum of all these values is equal to this one. And that actually, on the Pascal's triangle, doesn't really matter that much. Mainly that k choose k plus k plus 1 choose k, all the way till n choose k is just n plus 1 choose k plus 1. An example, 3 choose 3 plus 4 choose 3 plus 5 choose 3 till 8 choose 3 is just 9 choose 4. And you just increase this number by 1 and increase this number by 1. Now, something that you have to be very careful of is that these first terms have to be the same. You cannot start at 5 choose 3 or something like that. If you do, although, you can still evaluate this pretty neatly. Basically, this is a generalization right here. And that basically states that, what if now instead we're trying to find just 5 choose 3 till plus 8, 6 choose 3 till 8 choose 3. So what if you only want this part? You don't want this part anymore. Well, we know the entire sum is 9 choose 4. And the sum of these two values, by the hockey stick identity as well, is 5 choose 4, right? We increase 4 by 1, we increase 3 by 1. So this is just 9 choose 4 minus 5 choose 4. Just these terms. And that's essentially what this generalization is stating. The sum of all the terms, including the ones from k choose k, is n plus 1 choose k plus 1. And then from k choose k to j minus 1 choose k, you increase it by 1, you increase the bottom by 1, that's j choose k plus 1 by the hockey stick identity. And this is a generalization, but you don't really need to memorize this because you can always just use this one and derive it by the method I showed. Now, choosing odd-even identity. This is crucial. Basically, what it states is that n choose 0 plus n choose 2, so on, for all evens is equal to n choose 1 plus n choose 3, so on, for all odds. So all odd values less than n, and this is equal, and that's very cool. Okay, you don't really have to worry about this kind of complicated version of this, but just remember that choosing evens equals choosing odds. And remember, it has to be all of them, not just whatever odds you choose and feel like using. Okay, let's take a look at an example from the AMC. A club consists of 11 men and 12 women, needs to choose a committee from its members so that the number of women on the committee is one more than the number of men on the committee. The committee could have as few as one member or as many as all of them, 23. We're asked to find how many committees can be formed. This is just an answer extraction we'll worry about at the end. Okay. Can we express this in terms of choosing identities, maybe? Let's take it all the cases. Well, there has to be one more woman than man on the committee. So let's take all the cases. 1 woman and then 0 men. That's the first case. Or 2 women, 1 man. Or 3 women, 2 men. All the time, it's just one more. So on, all the way till 12 women and then 1 man. 11 men, sorry. Because it always has to be one more. How can we count this? Let's take it the first case. We have 12 total women, so we must choose one of them to be in the committee. And 11, we just choose 0 of them. 11 choose 0 or just 1, right? Next off, we have 12 total women, and from there, we must choose 2 of them for the committee this time. So 12 choose 2. And this time, it's 11 choose 1. And so on, all the way until 12 choose 12. There's 12 women, we select 12 of them, times 11 choose 11. Interesting. Now, how do we evaluate this? Well, this isn't Vandermonde's, but it does look a lot like Vandermonde's. The sum of the products of choosing expressions. Maybe we can convert it to Vandermonde's like I showed earlier, using a manipulation? Well, we know that 11 choose 0 is equal to 11 choose 11. 12 choose 1 times 11 choose 11. Let's just see what happens when we do this. Because we can always manipulate between n choose k and n choose n minus k, always. Next off, 12 choose 2. Now what if we do 11 choose 10 instead of this? And so on, 12 choose 12, and instead of choosing 11, we just choose 0, not to be there. And this is exactly Vandermonde's identity. This is 23 choose 12. Because our total is 23, and we're always dividing the 12 people between the 12 and the 11. Okay. And basically what we're doing is we're selecting all possible combinations. And keep in mind here that it's not possible to have 12 in the 11 choose 12, because that would mean 12 choose, that's not allowed, and that's in our choosing definition. That would be basically nothing, So essentially what we're doing here is we have 12 total to distribute between the two to choose, and 12 choose 1, 11 choose 11. They both have to choose a total of 12. So in total, it's just having 23 things and choosing 12 of them. So if we have 12 red dots and 11 blue dots, it's the same as just choosing 12 any dots or choosing by each type. So we have one blue dot, one blue dot, two blue dots, three blue dots, so on. And that is the choosing expression over here. And that's just like I explained for Vandermonde earlier. So 23 choose 12, our answer is 23 plus 12, 35. Now there's actually an even simpler way. Basically, let's say that we're selecting X men and X plus 1 women. Instead of counting the number of ways to choose X men and choose X plus 1 woman from 12, let's count the number of ways to not choose 11 minus X men, because there's 11 total, so we choose 11 minus X of them not to be in the committee, and the rest just go to the committee. And we just simply choose the X plus 1 woman to be on the committee. In total, we're choosing a total of 12 people, and that's no matter what. So out of the 23 total people, we just choose 12 of them. 12 of them, either women to be chosen or men not to be chosen. And the rest of the men will be chosen, the rest of the women will not be chosen. So this works for any choice of 12. So it's just 23 choose 12 by this logic, because there's 23 total men and women. Isn't that cool how we basically kind of derive Vandermondes, except we use a simpler shortcut? But either way, we get the same answer of 35. And now we're about to see another powerful identity in action. Find the remainder when 3 choose 2, plus 4 choose 2, all the way till 40 choose 2, choose 2. Okay. Well, how do we express this? I mean, we're not going to evaluate each of these individually. At least I'm not going to, because that would take at least another year, maybe till the 2023 AMCs. Let's express this as a variable. Let's say we're talking about n choose 2, choose 2. Okay, now I'm not about to deal with this because we don't really know any combinatorial identities for something choose another thing. So let's just write this algebraically with our choosing formula. That's just n choose 2 times n choose 2 minus 1, and that all of that over 2. Okay, now let's simplify this. We know n choose 2 is just n times n minus 1 divided by 2. N times n minus 1 divided by 2 times that minus 1. So n times n minus 1 divided by 2 minus 1 all over 2. Let's simplify this even further so we can get something a little bit simpler to work with here. Well, let's multiply the numerator by 2, or by 4 for that matter, and the denominator by 4, so we can clear these denominators over here and just move them to the actual denominator. So multiplying by 4 to the numerator and the denominator, we get n times n minus 1 times n minus 1, because we multiply by 2 to this term and 2 to this term. And 2 times n minus 1 over 2 is just n times n minus 1. And 1 times 2 is, well, just 2. So we're left with this, and divided by 2 times 4, or 8. And notice that n times n minus 1 minus 2, just n squared minus n minus 2. This seems like a oddly factorable quadratic, so we can actually, turns out it's factorable, n minus 2 times n plus 1. Okay, that seems like a lot easier to work with. We've got n times n minus 1 times n minus 2 times n plus 1. What do we do from here? Like, we could expand it and then use a bunch of formulas. That does not seem very neat of a solution. Can we maybe make it another combo identity? Well, what is n minus? Notice that this is just a product of all the numbers from n minus 2 to n plus 1. N minus 2 times n minus 1 times n plus 1. Can we rewrite this maybe? Of course, we have to divide by 8. Well, this is simply going to be equal to, we can actually, what we can do is rewrite this as n plus 1 factorial over n minus 3 factorial. Why? Because then the remaining terms that don't cancel out are n minus 2 times n minus 1 times n plus 1. So this right here is this part here. And of course we have a 1 over 8. The reason we write this is because, well, they're consecutive numbers. We might as well express it as factorials. Now, we're oddly close to the expression for choose. Can we somehow make this a choose term? It's almost looking like n plus 1 choose 4. Very close, except it's missing just one term. And that term is 4 factorial. So, as you can see, n plus 1 choose 4 is equal to n plus 1 factorial over 4 factorial over n plus 1 minus 4 factorial, which is n minus 3 factorial. Wow, that means that 24 or 4 factorial times n plus 1 choose 4 equals this quantity over here that we're looking for right here. That's interesting. That means this is nothing but 1/8 times 4 factorial, which is 24, of course, times 24 times n plus 1 choose 4. And this is just equal to 3 times n plus 1 choose 4. But the problem did not ask for it in terms of n. It's asking for an actual answer. And it's asking for the sum of this quantity from 3 to 40. 3 to 40. Let's see what we get when we write this. It's 3 times, well, we're going from 3 to 40. N equals 3 to n equals 40. So we're going from 3 to 40. So 4 choose 4. N plus 1 choose 4. When n is 3, n plus 1 is 4. All the way to for n, when n is 40, n plus 1 is 41. 41 choose 4. Okay, now what's the sum from 4 choose 4 to 41 choose 4? Is that an identity maybe? Maybe the one that was a hockey stick? The hockey stick identity? Because we're summing from 4 choose 4 to 41 choose 4. It starts at 4 choose 4. We increase this by 1. We increase this by 1. This is 3 times 42 choose 5 by the hockey stick identity. Now, let's simplify. 3 times 42 times 41 times 40 times 39 times 38 over 5 factorial, which is 120. This cancels 3, this cancels, and now it seems like we're left with just this to evaluate over here. Okay, let's do this multiplication now. But wait, are we going to really multiply this out? I'm not going to multiply it out. I'm going to use a shortcut. And that shortcut, difference of squares. 41 times 39 equals 40 plus 1 times 40 minus 1, which is 40 squared minus 1 squared, or 40 squared minus 1. 38 times 42 equals 40 plus 2 times 40 minus 2, which by difference of squares, 40 squared minus 2 squared, which is just 4. So now we just have to multiply 40 squared minus 1 and 40 squared minus 4. This is 1600 minus 1, 1599. This is 1596, 1600 minus 4. Notice the problem only asks the remainder when divided by 1000. So we can just ignore this digit because it only matters the digits over here. And now, again, are we going to multiply 599 by 596? No, we're not going to do an ugly computation. We're going to use more shortcuts. That's 600 minus 1 times 600 minus 4. And this is 36,000. 600 times 600 is 36. 36 with 4 zeros. So 360,000, sorry. Minus 1 times 600. Minus 4 times 600. So minus 5 times 600, which is minus 3,000. Plus 4 at the end. But we are asked for the remainder when divided by 1000. So these terms are both multiples of 1000. They don't matter. The answer is just that leftover 4 at the end. All alone, the answer is just 4. Now, let's move on to geometric counting and geometric probability. So, combinatorics is not geometry, but sometimes it can be taking place on a geometric situation. And that's what we'll explore in the next video over here.